Hi everyone, my name is Jessica. I'm currently a senior studying mechanical engineering in the College of Engineering, and today I'll be presenting to you about the development of a dynamic cushioning system with continuous piezoresistive sensor feedback for pressure injury prevention and treatment. So that's a really long title, so I thought it'd be a good idea to first break it down into the problem. So what causes pressure injuries? Pressure injuries are caused when 32 millimeters of mercury of pressure are applied to a contact area of about 2 hours. And because of this, medical attendants and caretakers need to constantly rotate patients every 2 hours to prevent the formation of these ulcers, as you can see on this diagram. An analogy of what 32 millimeters of mercury feels like is if you have the weight of a standardized volleyball on a surface area of about 1 inch squared, so about this much. So that's not an entirely extreme amount of weight, but it's still significant enough to cause really big damage to the body. So why does this actually matter? There are millions of pressure injuries reported per year in the US alone, with billions of dollars in med hospital treatment costs dedicated for the treatment of these pressure injuries. Additionally, there's a significant increase in the death rates of vulnerable populations. And yet, despite the large magnitude of all of these statistics, there hasn't been any proven cushioning system that can successfully treat or prevent the pressure injuries. So this is where our goal for the project comes in. Our goal for the project was to develop the first cushioning system that removes the need for human intervention in the prevention of pressure injuries. The way that this works is that each one of these cells, as you can see on the right diagram, will modulate up and down in pressure, sort of like a rubber spring, based on the amount of air that's pumped into it underneath. The amount of air that's pumped into it is quantified by the pressure sensors that lie underneath each one of these bellows. So in this presentation, I'll be taking you through each one of these components in the module. For our prototyping purposes, we actually went for a 4x1 module instead of the 10 you see here. So a little bit of a shortened module just to make sure that we could confirm the functionality of the overall device. So the first part of our module is our piezoresistive sensors. And for those who are unfamiliar with the sensors, these sensors quantify force by sensing the corresponding change in electrical resistance of semiconductive materials. In our project, we chose to use Velostat material, which is a conductive sheet made out of polymeric foil impregnated with carbon black. So this is a really inexpensive material that was really great for our prototyping purposes. Moving on to our design process for the sensors, we first began with a through mode sensor, which is more sensitive to lighter forces and obviously a lot more bulky than the one that you can see on the right, which led us to our final design for the sensor, which was a shunt mode sensor with metallic traces or interdigitated fingers. This allowed us to have a higher reception to a greater range of different types of forces, and that was really satisfactory for our purposes. Furthermore, here's the data on our accuracy of these sensors. We were able to use the Instron microtester at the BIT facility in BU to conduct these accuracy tests. And the way that this works is that in the bottom right, you can see a photo of the arm that is used to press down on the sensors, and that information is read in to our computer. And as you can see on the graph, you have a very close fit, so we're really satisfied with these results. Moving on to our next component of the device, which is our fluid cells. So just for size reference, each one of these cells is about the size of a toilet paper roll, so not too big. These are based on the size of the average pressure ulcer, so the size about 1.5 inches. And like I mentioned before, you can think of these cells like a rubber slinky that can move up and down depending on how much air is pumped in and out of the device. For materials, we chose to use Dragon Skin 10, which is a platinum cure liquid silicone compound that is both skin safe, so great for our medical mattress purposes, but is also fast curing, so really great for a rapid prototyping process. Moving on to the design of the fluid cell itself, so the geometry, we first began with a through hexagonal fold design, so these are hexagons all the way through. We found that the corners of the hexagon, due to the complex shape, increase the risk for air bubbles when molding, as well as increase the risk of tearing when removing these from the mold, so we decided to stray away from that design. The middle design you can see here, we really took inspiration from HVAC systems and medical breathing tubing because those both use compressible tubes that have the same movement or mechanism that we wanted. But we found that the twisting motion of the coil design really fell outside of our exclusively vertical motion that we were hoping for, so we again strayed away from that design. We ultimately ended up with a through circular fold hexagonal cap. So starting off with the hexagonal cap, we found that if we were to move to a circular shape, we would reduce the support surface area by 20%, and we really wanted to maximize that, so we kept the hexagonal cap. Additionally, hexagons have a really unique geometry where if you have them in an array, you reduce the amount of space between each of these shapes. So you can think of that over a circle. There's a lot more empty space if you were to put them side by side. As for the circular folds, we were able to simplify that design while still maintaining the same compressibility mechanism because it is, again, just in the vertical direction. This also reduced the risk of air bubbles and tearing, like I mentioned earlier. The next component of our device was the control board. So the metrics of success listed on this slide relate to a 300-pound person, 50% fail rate of the device. We wanted to opt for a very conservative fail rate just because of underserved medical communities. They don't always have the funds to replace an entire system. So we wanted to make sure that even if this device were to degrade over time, people would still be able to operate it and support the prevention of pressure ulcers. Additionally, our metrics of success really prioritize the fast communication between the different components in the stack-up. So we would like to have an almost instantaneous response to any detection of pressure that falls outside of the accepted range. Additionally, because this is a modular system, we want to make sure that the modules can communicate with each other as they are built out into a larger system. Going further into our next goal, which is integration, this is a picture of our first preliminary prototype. So you can see it's a little bit unstable. A little bit of the cells are in as close of an array, and this leads us to the pictures of our next design. So you can see a very stark difference. Instead of a module of 16, we opted for a row module, so only 4. And this also allowed us to save on material cost by reducing the size of the module and then allowing this to be built on further. Additionally, by facilitating manufacturability, by reducing the number of components, by incorporating the sensors into the control board, and also making sure that these cells were lower in material costs by modifying the molds, we were able to both reduce costs but also reinforce a modular design. By saving on these material costs, we were able to upgrade to different types of technology as well. Additionally, as you can see on the bottom right, there's mates that are on the sides of these casings. We took inspiration from Japanese woodworking processes that actually don't require any adhesives like glue or screws to join the surfaces together. So this allowed us to kind of create a Lego-like system that was customizable. So people would be able to build each one of these modules out into a wheelchair cushion or a medical mattress, depending on the size and their own individual use cases. Additionally, because of this modular system, people can just replace one module instead of the entire system. Currently, medical mattresses on the market require people to replace the entire system if there is a faulty cell or a faulty bag within the mattress, and those run at a cost of $50,000 and up. So we wanted to make sure that this was both ergonomic and also catered to real patients. As for our next steps, they are to expand the 4x1 module into a 10x1 module to look at the functionality of it as a medical mattress. We also have a patent pending on this technology. And in conclusion, our project has 3 functions. It serves as a mattress, diagnostics tool, and caretaker in one. In our goals to treat pressure injuries and remove the need for human aid and repositioning, we also projected to save hospitals thousands of dollars per patient per month. Thank you.
I was just wondering what the inspiration behind your project was, if there was any.
Yeah, so actually one of my team members, family members actually became quadriplegic over the past couple years. This means that they are immobile and they're unable to move by themselves. So their family members had to take on the responsibility of getting up in the middle of the night every 2 hours to rotate them to prevent these pressure ulcers from occurring. And as you can imagine, this is a really significant personal burden, but also financial burden if you aren't able to hire a caretaker. So this solution really is aimed at both personal care and in hospitals to reduce those costs.
Can you talk a little bit about the manufacturing process for the actual hexagonal cushion?
Yeah. Let me go back to the slides. So here you can see that the cell itself, so it is empty in the middle, so you can pump air through it. And we used a 3-part mold, so 2 sides and then 1 in the middle just to have like kind of like a coating on the middle part. So we were able to use that, and we used the 3D printing process for rapid iteration. But in the future, we want to have like a CNC type mold, so like to increase the durability and for like mass manufacturing, like in a factory setting.
Great presentation. How does the air supply work? Like,
Yeah, let me go back to the stack up. So the pressure sensors fall right underneath the air cells, and then the solenoid valves have tubing that connect through and outside of the casing. So if you can see this image there, you see the hole in the bottom right, like underneath everything. That's where the tubing will come out and connect to the air pumps.
okay, I see. Yeah, awesome.
I have an implementation question.
Yeah.
So this seems like an incredibly elegant and feasible design, right? That would seem to be immediately attractive and adopted. Can you envision any obstacles to its use and kind of widespread implementation?
Yeah, so the medical mattresses that claim to be effective in the prevention of pressure injuries on the market are currently owned by like 3 really large companies. So there's always that element of competition and being able to kind of like beat them out as the underdog. And again, we're still in like the prototyping phase, so we still have a little bit of time before we can actually like take this to market. So I think the main proponent of like competition is really like big for us as right now, but I think the functionality of everything still needs to be refined a bit more, but I think that's the main, yeah.
Do you have a question?
No,
Do you have time for one more?
Okay, thank you.
Thank you so much.